Hello, this is Ezra with AP Calculus AB and BC Review. This is Unit 6, Integration. In this unit, we look at area under the curve. We look at how we approximate that area. We'll look at something called Riemann sums and when they go to infinity. We look at the fundamental theory of calculus, 1 and 2, and antiderivatives. And then we take a look at integration techniques, and then for BC only, we have more advanced integration techniques and improper integrals. So let's get started. So area under the curve is essentially what your integral is. So we can relate it to the past unit, which was about rates. So if we have a function like this, and we say this is the rate at which water enters a tank, then the area underneath the curve is the amount of water that enters the tank. So why does this make sense? Well, for instance, if you have just a function where it's a line, right? This is the rate at which water enters a tank in this function, right? This is y equals 3. So it's at a constant rate of, let's just say, 3 liters per minute. So after 1 minute, if it's at a constant rate of 3 liters per minute, you can expect it to have 3 liters in the tank. After 2 minutes, it's 6 liters in the tank because 3 liters per minute times 2 minutes is 6. So if we have this function, the area beneath its curve and the x-axis seems to be the amount of water that's in the tank at any given time. So after 10 minutes, it's just going to be 10 minutes times 3 liters per minute, which is 30, which will coincidentally be the area underneath the curve between 0 and 10. So what does that look like for this function? Well, let's say this is water entering a tank, and this is negative sine x plus 2. Alright, so if this is at x equals pi, then the rate at which water enters the tank is modeled by a function like this. So that means at x equals pi, it's going to be at 2. That means at x equals pi, water is entering the tank at 2 liters per minute. But down here, at x equals pi over 2, then if you plug pi over 2 in here, then your rate is going to be 1 liter per minute. So that makes sense with this function. It starts at 2, and then it goes down to 1 liter per minute, then it goes back up to 2. So the area under this curve, as we've observed before, is the amount of water that enters between 0 and whatever time you have, or whatever x value you have. So how could we approximate this? Well, I'm going to look at the function x squared, because it's a very nice function for looking at approximating. So this is our function x squared, and I'm going to say that this is 1, this is 2, this is 3. So to figure out the area under the curve, we're going to look at something called Riemann sums. So there's 3 types of Riemann sums, and then there's one other type of approximation. So there's left Riemann sums, right Riemann sums, and then midpoint Riemann sums. So what do these all look like? Well, a left Riemann sum will have the left corner of the rectangle on the function. So what do I mean rectangle, right? Well, if you wanted to approximate the area under here, you could draw little rectangles underneath it, and this would like partially give you the area under the function. It might overestimate or underestimate, and that we'll talk about in a second. But if you make smaller and smaller rectangles, then you'll get a more accurate area. So that's what Riemann sums are. It's making rectangles under the curve to approximate it. So what a left Riemann sum looks like, it has the left corner of these rectangles on the curve. So left Riemann sum, I'm going to draw it in red, would look like this. The left corner of the rectangles is on the box. So if I wanted to approximate the area between 0 to 4, let's say, you would have these three rectangles, and then you can add up the area, because we know the height of this rectangle will be 1, because 1 squared is 1. The height of this one's 4. Then the height of this one is 9. You get these by plugging, x equals 3, x equals 2 into there. Okay, so that's a left Riemann sum. Now, a right Riemann sum, I think you can imagine, would have the right corner of the rectangle on the function. So, a right Riemann sum would look something like this. So this here, we're approximating the area from 0 to 3. And then a midpoint Riemann sum, you might be able to imagine, is in the middle of the two. So you take the value between 0 and 1 halfway up, and then you draw your box there. So if our x equals 2 is right up here, then we take the box halfway through it, right around here, halfway up to approximate it. If our 3 is up here, then we take a box about here to approximate it. So, just to reiterate, left Riemann sums have the left corner of the rectangle on the function. Right Riemann sums have the right corner on the function, and midpoint is in the middle. Alright, there's one more that we can look at. They're called trapezoidal sums, which essentially put a diagonal that sort of matches the curve. So here, you'd have a line here that goes up to x equals 1, y equals 1, and then you have a diagonal to x equals 0. Same here. You have a line here, and then you have a diagonal here. Then again, a line here, a diagonal here. So now these are much more accurate than these Riemann sums. And the formula to find the area is just a trapezoid formula. So the height of this side is 9, because x equals 3, y equals 9. The height of this side is 4. So that means that the area of this trapezoid is 9 plus 4 divided by 2, and then times your delta x, which is 1. So what is the general formula for a trapezoidal sum? Well, you have the y1 plus y2 over 2 times delta x. So that means if I wanted to do a trapezoidal sum from just 1 to 4, or I guess 1 to 3, it would look more like this. So it would be less accurate, because remember, the less or the more rectangles you take, the less area those rectangles have. When you add them all together, you're going to end up with a more accurate estimate. So when are these increasing and decreasing? Or when are they an overestimate and underestimate? Well, for left and right Riemann sums, it depends on if they're increasing or decreasing. So, if we have a right Riemann sum on the increasing part, as you can tell, this is going to be an overestimation. We have all this extra area over here above the function. And then vice versa. For left, it is pretty clearly an underestimate, because we have all this area that's not in the function. Now, midpoint and trapezoid do not depend on increasing or decreasing. If I show you over here, there's still area over the curve over here, and then there's area over the curve over here. So it's an overestimate on both of these things. The overestimate and underestimate actually depends on concavity for midpoint and trapezoid. So trapezoids are an overestimate when the function is concave up, and an underestimate when it is concave down. Midpoints are overestimates when it's concave down, and underestimates when it's concave up. So if I were to do one full demonstration, these are left Riemann sums, which you can see are overestimates on decreasing, and then left Riemann sums, underestimate on increasing. Now I'm going to use this different color to show you that right Riemann sums are underestimates on decreasing, and then overestimates on increasing. Okay. And then on I'll give a concave down graph, trapezoids are overestimates on concave up, and then they end up being underestimates on concave down. As you can kind of see here, there's this extra area. And then midpoints, if it were like this, since it's concave down, it has more area over the curve than this area that is not approximated by the curve. And same thing over here. More area over here than area under here. More area over here than area under here. So that's why it's an overestimate on concave down. And then on concave up, you have more in this than over here, which it might be hard to tell, but you do. Which is why it is an underestimate on concave up. So now, what happens if we were to take this to infinity? Well, if you have, let's just do a random function like this. If you had smaller and smaller rectangles, eventually, the smaller rectangles you got, you'd have less and less area over here, in which case you would have the exact area under the function. So how could we write that? We could write it as, you have to put a limit because there's infinity. The limit as it approaches infinity of our summation. So we're going to just say k equals 1. Starts at one whole rectangle to approximate it. And then we go to n of whatever function we have. So this is essentially f of k delta x times x delta x. So what does this mean? We're increasing the amount of rectangles over here. So if it is 100, then we're going to have 100 mini rectangles inside. So we can actually convert this to an integral form. Now this formula is slightly different because integrals can be like from 3 to 7, right? It doesn't have to be from 0 to a number. So what we actually write this formula as is f of a plus delta x k times delta x. So what this is is the integral from a to a plus delta x and then of f of x dx. So this delta x is actually whatever your delta x is over n. So if it's like 3, then it's going to end up being 3 over n. So what do I mean by that? Well, if you have, let me give a Riemann sum, f of 3 plus k 3 over n times 3 over n. 3 over n is your delta x. Your delta x is going to be over n when you have like your infinite Riemann sum. So this, if you put your k equals 1, I'm just going to write infinity, but it's always going to have this sort of thing. Limit as n approaches infinity, and you have n on the top. I'm just going to write infinity because it's easier. But now you have your f of 3 plus k, 3 over n. This is just going to be your integral from 3 to 6, because this is your 3 is your delta x, so it's from 3 to 6 of f of x dx. So let me give an example. If you have sine 2 plus delta, or 2 plus k 3 over n times 3 over n. This integral would be, you take your a value, that's your first, 2, your delta x, so 2 plus 3 is 5, of sine of x dx. This is correct. However, there's a second way to write this. You need to know that there's 2 ways to write it, because on the multiple choice section, you will not always get the same way. This, I'm just going to copy this over. Guess not. Can also be written as not taking this a value into account. So, if you don't take that a value into account, pretend that 2 is part of the function, you will still have your 0 to 3. This is still your delta x, except now you'll have sine 2 plus x dx. These are equivalent, these two integrals. So you can either use this as your a value, put it into here, and then do 2 plus 3 for your a plus delta x. Or you can think about your a value as 0, put that on the bottom, use your 0 plus your delta x, so 3 on the top, and then this value inside becomes part of the function. So there isn't always, but usually is a question where you have to convert these infinite Riemann sums to an integral. So knowing how to manipulate your a value can get you the right answer. And it's always going to be on a multiple choice as well. So now we can talk about integral rules. So if you have an integral a to b, and then you have a, this is some not a, we're going to use k as a constant, f of x dx. Always put your dx. If you're on an FRQ and you don't put the dx, you get no points for that integral. So this k can actually be moved out. So these are the same thing. For instance, if I have the integral from a to b of 3x cubed, this is the same thing as 3 times the integral from a to b of x cubed. Another rule, integrals can be split up with subtraction and addition. So f of x plus g of x can be the integral from a to b f of x plus the integral from a to b g of x. This works. And the same thing will work if this was a minus sign. However, it does not agree with multiplication, or division. So do not do f of x times g of x is this integral times this integral. That does not work. Same with f of x over g of x. It does not work. One more thing is that if you have an integral which is b to a, let's say, and we're going to say that b is greater than a, then you could write it like this, but the more proper way to write it is negative a to b. These are equivalent. So you should always convert relationships like this into this sort of integral. So if you have the integral from 5 to 3 of f of x dx, you should always, to not mess things up, always write it as negative integral from 3 to 5 f of x. So those are the rules for integrating. Now we're going to look at the fundamental theorem of calculus 1 and 2. So 1 is the one that people mess up more on. So this is saying if you have a function, this is called an accumulation function. From some number down here, it doesn't matter, of f of t dt. That means that if you have a function and then it says like g of x equals this function, that means g of 3 is just the area under the curve from this constant to 3 of this f of x or f of t function. So the first fundamental theorem of calculus says that if you take the derivative of this function, you will get f of x. Pretty simple. If you have a function and you integrate it and then take the derivative, you just get back the function. This is because integrals are antiderivatives. It's the opposite of a derivative. So these two essentially cancel out, and this x just goes into here. However, one thing that people forget about is that if you have a to u, we're going to say this is some function u, some nonlinear function u. When you take the derivative, you not only plug this nonlinear function u into here, or linear, actually, it can be, f of u, you have to multiply it by the derivative of u. So, if you have, for instance, 0 to x squared of f of t dt, and then you take the derivative of it, you're going to get f of x squared times 2x. This relationship is what people always forget. There is, again, usually a multiple choice problem on the test where you will have to know this, where you will have to times it by the derivative, and if you don't, you get it wrong. So, watch out. The second fundamental theorem of calculus is much easier. So, if you have any definite integral from a to b of some function, f of x dx, we're going to say that f of x, that is the derivative of f prime of x, lowercase f. So, this is just f of b minus f of a. So if you have some function, some lowercase f function, and you take the derivative, and that gives you, your big F function. Then from a to b, if you integrate it from a to b, you just plug in little f of b minus little f of a into the original function. So, how are we going to do that? Well, first we're going to have to look at how to take the integral of some things. I'll just do 2x for now. So, this is an indefinite integral, no bounds. So, if you have the integral of 2x, first thing we're going to talk about is the power rule. So basically, if you have x to the n and you integrate it, it is x to the n plus 1 over n plus 1. This is the reverse of the power rule, where you have x to the n minus 1 and then you bring the n to the front. This is the exact inverse of that. So, the integral of 2x is 2x to the 1 plus 1 over 1 plus 1. So 2x squared over 2x squared. So, using our fundamental theorem of calculus 2, if I said, oh, don't forget your plus c, by the way. If I said the integral from 0 to 3 of 2x, you would have to take x squared, and then you have to do 3 squared minus 0 squared, which is ending up being 9. Now, on a definite integral, you don't have this plus c. You have it on the indefinite integral, because if I integrated 2x and got you x squared plus 9, whatever, if you take the derivative of this, this would just give you back 2x. The constant goes away. So, if you have x squared plus any constant, if you take the derivative, it's gonna go back into 2x. That's why you have that plus c here. Because this function can be x squared plus any arbitrary constant. It will always turn back into 2x. However, in a definite integral, if I had 0 to 3 of 2x dx, if you plugged in c, you would get 3 squared plus c minus 0 squared plus c. And then this is 9 plus c minus c. These c's will cancel out because of this negative sign. So on a definite integral, you end up not really caring about the plus c. There is a plus c, but you never write the plus c because it always will cancel out internally. Let's look at another example of a power rule before we move on. You can, of course, like I said before, add things in an integral. So if you integrate this, this is the same thing as integrating all of these separately and adding them together. Integration agrees with addition. So let's just do the power rule on each and every one. 1 over 3x to the 3 plus 1, which is 4, divided by 4. So if you're following, x to the 4th over 12. Plus 9x squared. 9 x to the 2 plus 1, which is 3, over 3. 9 divided by 3 is 3. So this is 3x cubed. 6x to the 1 plus 1, which is 2 over 2. 6 over 2 is 3. So this is 3x squared. And then don't forget the plus c. So the power rule is really that simple. It's just the opposite of the derivative power rule. Now, we're going to look at the most important integration technique, which is U-sub, and this shows up all the time. So one thing we're going to talk about, just briefly, is that the integral of 1 over x is ln x. Now this is because the derivative of ln x is 1 over x. So this relationship is the most important relationship in calculus. This shows up numerous times. You're going to see it all throughout this video. You're going to see it all throughout future videos. This relationship is super important. So knowing that is important. And then e to the ax, if you integrate it, you get 1 over a e to the ax. This is because if you have, let's say, e to the 2x and you take the derivative of it, you get 2e to the 2x. So then, if you integrated 2e to the 2x, you would get 1 over 2 times 2e to the 2x, and then these cancel out. So then you get your e to the 2x back, plus c. So, those two relationships are very important. Now, U-Substitution is hard to get at the start, but once you get it, it becomes natural. So, we're going to start out with something like this. So now, how would you do this normally? Well, you don't really have anything. It kind of looks like ln, which is what we will be using, but you can't really integrate this without U-Substitution. So what are we going to do? Well, this whole denominator can just be shoved into one variable, which we're going to call u. So we're going to say u is equal to 2x plus 4. Right. Now, if you can't integrate something like u with respect to x, this doesn't make any sense. So how do we change dx into du? Well, if you have u and you take the derivative of it, du over dx is going to equal 2, because we have 2x. 2x plus 4, the derivative of 2x plus 4 equals 2. So now, what we can do is multiply this dx onto this side, and then we'll have du equals 2 dx, or du over 2 equals dx. So this is our replacement for dx. So now we can, instead of having dx over here, we can have du over 2. Remember what I said about constants though? This is 1/2. So this can actually just be moved out. 1/2 integral of 1 over u du. Now, the integral of 1 over x is ln of x. So, the integral of 1 over u is ln of u. Absolute value of u, I should say. So is this our answer? Almost, but remember, you need to plug in your 2x plus 4, because this is our u. You need to plug this back in. So our actual answer is 1/2 ln 2x plus 4 plus c. Which may seem like a lot right now, but we're going to keep doing practice, and eventually it will feel more natural. So let's take something that's not like a fraction or anything like that. 8x minus 12. And then you have 4x squared minus 12x to the 4th. So if we wanted to integrate this, in theory, you could multiply all of this out. But that's ridiculous. I mean, you have to the 4th power over here. That's gonna take you so long to multiply it all out, and very easy to make mistakes when you're doing that much multiplication. So, what we're gonna do is we have this thing. So, 4x squared minus 12x, this looks like a crazy problem, but when you take u as 4x squared minus 12x, the derivative of 4x squared minus 12x, we figured out that du over whatever, like u prime, equals dx. The derivative of u du over the derivative of u equals dx. So this is just a way to quickly do u sub. So we can say du over, what's the derivative of 4x squared minus 12x? 8x minus 12 equals dx. And would you look at that, that's just this. So now we have 8x minus 12 over here. And then we times it by u to the fourth, du over 8x minus 12. Now this and this completely cancel out. So now you have u to the fourth du, which is just 1/5 times u to the fifth plus c. And then remember, you have to resubstitute in your u. So this answer is just 1/5 times 4x squared minus 12x to the fifth plus c. Okay, so such a daunting problem right here, where you'd have to do so many minutes of multiplication, can be simplified into just 3 steps. You find your u value, you put du over the derivative of your u, and then you can from there simplify. We're going to do some more practice because, like I said, this shows up on the test at least once, very often multiple times, on both A, B, and BC. So, I got some more problems here. 3x squared minus 4 over x cubed minus 4x plus 1. Alright, take a second, see if you can think of this. This problem is much, much easier than it looks. You set your u equal to the denominator. Usually that is how it's going to go. And now, du over 3x squared minus 4 equals dx. And, would you look at that? You have a 3x squared minus 4 over there. So, you have 3x squared minus 4 over u du over 3x squared minus 4. These cross out, you get 1 over u du, which we know is ln of u plus c, which we know is ln of x cubed minus 4x plus 1 plus c. I did that quite quickly, but it's the same principle. You have a big, ugly function, which you can just set as a u variable, and then eventually it will end up canceling out something else in the function, making it possible to integrate. And then you can put it into here. Now, I have 2 more examples to show you. One of them is something like this. Now this, if we can use our deduction skills from the derivatives unit, the derivative of sine is cosine, so that means the integral of cosine is sine. And then the derivative of cosine is negative sine, so the integral of negative sine is cosine. Here we have the integral of sine, so the integral of positive sine, if we just take this negative out, we can move this, and now the integral of sine is negative cosine. Alright, sweet. Now that we know that, we can find our u value. So, I think at this point, it should be getting easier to figure out what the u value is. Here, it's that bigger function that's inside something or whatever, right? So u is x squared minus 4, and that means du over 2x equals dx. So we have the integral of x sine of u du over 2x. All right. Here we can cross out these x's and move this 1/2 to the front. So we have 1/2 integral sine u du. All right. Now 1/2 negative 1/2 cosine u, because we have the negative cosine, plus c. And then final step, take our u and plug it back in. Then we have negative 1/2 cosine x squared minus 4 plus c. This becomes natural after a while. You'll be able to do problems that quickly. Now here is a little bit more of an unorthodox one. E to the square root x over square root x. Looks unorthodox, but same concept. How could you cancel out something here to make this possible to integrate? Well, what is the derivative of square root of x? X to the 1/2 minus 1, then you have the 1/2, is 1/2 x to negative 1/2, which is 1 over 2 root x. You can get that from the power rule of the derivative. So, what if we subbed in square root of x as our u? Okay. But here, we have a second square root of x. Do we set that as u? You could, but in this case, it's better to not. So if we have e to the u over square root of x, what would our dx be? Du over, what is the derivative of this? Well, we just figured out 1 over 2 root x, which ends up being 2 root x du equals dx. Hold on. 2 root x du is our dx. And now, since we didn't sub this as a u, these cancel out. And then we just have 2 integral of e to the u du. Integral of e to the u is just e to the u. So you have 2 e to the u plus c, which is 2 e to the root x plus c. So in harder problems like this, sometimes you don't replace the bottom. You don't replace everything with that, so it makes it easier to cancel out. You got to figure out which things cancel out. Sometimes it will be very obvious. Sometimes you'll have a little bit harder problems like this. But in the end, it's just figuring out what needs to be replaced so you can sub something out. Next, we're going to move on to a more niche sort of technique. So these next two techniques do not always show up on the test. So first we're going to have 2x squared plus x over x minus 1. Alright, we're integrating this. Can we U-sub here? No, it's not really going to work. Is there any division rules we can use? No, because, again, division with integrals, they don't agree. So, what we have to do here is literally divide these functions with polynomial long division. So, I'm going to use synthetic division because we have x minus 1 as a divisor. So, 1 over here, we have 2 for our x squared term, 1 for our x term, 0 for a constant. So I'm going to bring this 2 down. 2 times 1 is 2, so 1 plus 2 is 3. 1 times 3 is 0, plus 3 is remainder of 3. So this is 2x plus 3 plus 3 over x minus 1. So now, this seems pretty easy to integrate because we can just power rule this. So, the integral of 2x, eventually you'll see that and just realize it's x squared because x plus 1 plus 1 is 2. Okay. So then we just have x squared So 2x to the 1 plus 1 over 1 plus 1. You'll eventually see this relationship and be like, oh, that's x squared. So we have x squared. The integral of any constant, again, you just add an x term onto it. So if you have the integral of 2, it is going to be 2x. And that's because 2x to the 0 plus 1 over 0 plus 1 is 2x to the 1 over 1. That's that relationship. It's just a power rule, but it can be a little bit confusing. So we're going to have 3x. And then here, since nothing is crazy about this, we just have x minus 1 on the bottom. You have 3 integral 1 over x minus 1. So you could u-sub this if you want to, but then you're just going to have du equals dx, because the derivative of this is 1. So instead of u-subbing, here's a little trick. If you have the integral of 1 over x whatever plus 9, as long as this x value has no coefficient to it, it's just 1, this will just be ln of whatever's on the bottom. So here we have ln of x minus 1 times this 3 in the front. So it's 3 ln x minus 1 plus c. And then this is your answer. This method is very occasionally on the test, but it is quite niche, so I'm only briefly going over. The other method is completing the square. So if I have something like x squared minus 4x plus 7, now can't u-sub, obviously, there's nothing up here to cancel it out, but here's what you need to recall. The derivative of arctangent is 1 over 1 plus x squared. But really, it is using u as our variable, because it can be arctan of 2x or arctan of x squared, is going to be u prime over 1 plus u squared. So the integral of 1 over a squared plus u squared equals 1 over a arctan of, not x, of u over a plus c. So if I were to give you 1 over 4 plus 4x squared, right? This u value is 2x, because 2x parentheses squared is 4x squared. So this would just be 1 over 2, because 2 squared equals 4, arctan of 2x over 2. So that's ends up being arctan of x. Alright, that's our brief overview of arctan. Now, how could we get a u squared plus an a squared? Now, what we have to do is look at these two terms. Ignore this for now, because we'll deal with that later. So, if we have x minus 2 squared, that gives us x squared minus 4x plus 4. So, this can be written as 1 over x minus 2 squared plus 3. Because here, if you add 3, then you end up getting this. So this can be rewritten as this. And now, integrating this doesn't seem that hard, because we have our arctan relationship right here. This is our u squared, this is our a squared. So this integral is just 1 over square root of 3, because square root of 3 squared equals 3. So our a value is square root of 3. Arctan of u, which is going to end up being x minus 2, over square root of 3 plus c. That is our completing the square method, because we take this and we convert it into some sort of square, and then this extra leftover number is ending up being our a value. And then you can just use an arctan formula to find it. Again, those two methods do not show up very often, but it is important to know them in case they do. So that is the end of all the AB material in Unit 6. Now, we're going to move on to the BC material. So we have three really main things. We have advanced integration techniques. So we have integration by parts, integration by partial fractions, and then integration of improper integrals, which is when an integral has infinity in it in one of the bounds. So let's get started with integration by parts. So I'm going to throw a formula at you. The integration of u dv equals u times v minus the integral of v du. So this formula is not going to mean anything to you. But let me show you what I am talking about. So, well, I'll leave this formula on screen, just so it's always there. But if I gave you the integral of x ln x, so now, although I said there's no multiplication relationship with integrals, this is the reverse product rule of the derivative. That's what you can view it as. So, what am I talking about here? With u dv, uv, v du. This doesn't make any sense. So, there's a acronym called Li8, which I'm going to talk about in a minute. But basically, you want an integral in the form of this, in form of u dv. So, for instance, in this integral, I'm going to say that my u is ln of x, and I'm going to say my dv is x. So what you want to choose for these ones is your u value you need to take the derivative of, so du equals 1 over x. And then your dv value you need to integrate, because in this formula you have a u, you have a v, and then you have a du. So you need to know what du is, you need to know what v is, and then you need to know what u is. So we have our u. Our du is just a derivative and then add dx to the end. And then our v is the integral of our dv. So 1/2 x squared. You know how to integrate x, and you know how to take the derivative of ln of x. So for any integration by parts problem, you need to create this relationship. These are the four corners of parts. You have your u and you have your dv, and then you have your du and then you have your v. It's picking your u and your dv, which is the main part of this, and memorizing this formula. So, how do you know what to pick your u and dv as? Well, you have this acronym, Li8, which stands for logs. Forgot the I. This is trig. This is exponential. This is arithmetic. And the I is inverse. Right. So the I doesn't come up very much. But I'm just going to leave it. So this is the one to pick your u as. So you start off with logs. If you have any logs in your function, which we do here, we have natural log of x, you want to pick that as your u. Because taking the integral of that, you don't really know the integral of that. So taking the derivative of a log is much easier. And then inverse is for inverse trig, like inverse sine, which we will talk about. We will be integrating inverse sine. Arithmetic is just any polynomial, x, x squared, whatever. Trig, sine and cosine. And an exponential is the last one. Avoid it if you can. Because, think about it, you're never going to be able to reduce an exponential to 0. Same with trig. That's why trig and exponential are at the bottom, because however many times you integrate e to the x, you're going to get e to the x. If you integrate 2 to the x, you get ln 2 to the x, and then you get ln of 2, ln of 2, 2 to the x. So however many times you take the integral or derivative, you're not going to be able to reduce that. So that's why you have this rule. So really, these first three are the only ones you should be setting as your u. In this case, log takes priority over arithmetic. So we set our u as natural log of x, and then our dv, the other one will just be dv, naturally, as our x. Anyways, with these 4 pieces that we just got, we just plug it into this formula. You do have to memorize this formula. There are mnemonics to help you online if you want to search them up. But here, you just have u times v. So u is ln of x, v is 1/2 x squared. So we're going to have 1/2 x squared ln of x minus the integral of v du. So 1/2 x squared times du, which is 1 over x dx. So this 1 over x crosses out one of the x's in the exponent. So now you have 1/2 x squared ln of x minus the integral of 1/2 x dx. Alright, integral of 1/2 x dx is 1/4 x squared. So your final answer is 1/2 x squared ln x minus 1/4 x squared plus c. This is your answer for this. Now, don't worry, we're going to do more, because this is weird to think about at the start. So, we have inverse sine of x dx. So, you look at this and you're like, what are we doing? There's no integration by parts here. Well, there is if you think about it in a different way. You do have two things multiplied here. Inverse sine of x and your dx. This is like a tangible thing in this case. So what do you do here? Well, using Lie, we're going to set our u as inverse sine of x, right? And then du is 1 over square root 1 minus x squared dx. Okay, fine. Now we're going to set our dv as dx. Okay, that means our v is just going to be x. So now, if you think about your dx as a tangible object, and you say dv is going to be your dx, then now you can see that it is integration by parts. So we're going to use the formula. uv, so x inverse sine of x, minus v du, so x over square root minus x squared dx. So now we're going to have to use another technique. We're going to have to U-sub this. So let's just take this part and move it down here. So integral x over square root, and we're going to replace it with u. u equals 1 minus x squared. So that means du is negative 2x. We cross out this x and this x. And now we can actually cross out this negative and this negative. So we're going to get 1/2 integral 1 over square root u du. This is u to the negative 1/2. So if we were to integrate this, you would get u to the negative 1/2 plus 1. So u to the 1/2 over 1/2, which I'm going to write as 2. So you actually end up getting 1/2 times 2 u to the 1/2, so square root of u. So these cancel out. So you end up just getting square root of u, which is square root of 1 minus x squared. So, since we moved this minus sign with this, we actually don't have that minus sign anymore. So now, this minus integral of x over square root 1 minus x squared dx, this just becomes x inverse sine of x plus square root 1 minus x squared plus c. So I'm going pretty fast because there's a lot of topics, but if you rewind, you can see the process that I did. But first, again, reiterating, you set your u and your dv as things using Lie8. Find your u, and then the other one is automatically dv. And then you do your du equals the derivative of u times dx. You replace that as your dx. And then from there, you can use the formula uv minus integral v du. Alright, so there's one more problem I'm going to do, which is a long one, and it is nightmarish for BC students, which is e to the x cosine of x. This is a classic problem. This has been given on the AP test before, and it is never fun. But you'll see why. So we have Lie8, right? But both of these fall into our bottom two categories, which are our never used categories. So unfortunately, we're stuck with using one of them. And in this case, trig comes before e to the x. E to the x is just a nightmare. So we're going to go, u is our cosine of x. Du is our negative sign. And then dv is e to the x. And then shocker, our v is going to be e to the x. So let's plug this in. uv e to the x cosine x minus v du, so integral e to the x sine x. And then because this is negative sine x, right, I'm actually going to take this negative out and put it over here, just to make things easier. Alright, so we've e to the x cosine x plus, okay, we have another one. So we have to parse it again. Sine of x du equals cosine of x. dv, again, e to the x. dx, and then our v is e to the x again. Alright, so taking this, we're going to move it down. So uv e to the x sine x minus v du e to the x cosine x dx. We just got the same thing that we were trying to solve in the first place, which is e to the x cosine x. So is this possible? Well, yes, with some algebra. So now, let's get rid of this stuff, all of this stuff. We know that e to the x sine x dx is this whole thing. So, let's actually just move this over. So, I'm going to get rid of this just to make the space. So, integral of e to the x cosine x dx is e to the x cosine x plus e to the x sine x minus itself. But if you think about the integral as like a variable, you can move this integral over to here. So now you have 2 times the integral of e to the x cosine x dx equals e to the x cosine x plus e to the x sine x. Because we're subtracting it, so you add it to both sides, and now this is possible. Now you just divide both sides by 2. And then now you have your answer. So if you want to integrate something which is like exponential e to the x and has a trig function sine of x, it will look like a repeating loop where it's just going to keep cycling through trig functions and e to the x. But eventually at some point you will have the same thing on this side and you can move it over, and then that can be your final answer. That's how you solve this. So this is a problem that I've seen before on the BC test, and knowing how to do it, honestly, knowing this relationship can just save you so much time. So that is integration by parts. Now, we're going to do some partial fractions. So, if you have the integral 7x over x squared minus 5x plus 6. So this is the friendly values method, which is, first, we can factor this bottom. We can split it up. So, integral 7x over x minus 2, x minus 3. Right. That's all well and good. Now, we still can't do anything with this until we split it up. So what we're going to define is that a over x minus 2 plus b over x minus 3 equals 7x. So why are we doing this? We want to split up this 7x and give some to the x minus 2, some to the x minus 3, if that makes any sense. So we want to split up this into two separate fractions, which we can then integrate by ln of x. So here we have to cross multiply this and then cross multiply this and this to get a times x minus 3 plus b times x minus 2 equals 7x. All right, we just did that. These are all equivalent. And now we want to solve for a and b in order to split this thing up into fractions. Because if we solve for a and b, then we will just have these two fractions be equivalent to this whole thing. That makes sense. Because if you have this plus this is 7x, then in one of the fractions, this and this will cancel out. And one of the fractions, this and this will cancel out. So we are going to substitute values in that make one of these 0 and give the other one a value. So first we're going to do x equals 2. If you sub in x equals 2, 2 minus 2 is 0. So this b goes away. So then we're going to have a, and then 2 minus 3 equals 7 times 2. Right? We just plugged in 2, which would cancel this out. Then we get negative a equals 14. So therefore a equals negative 14. All right, that's cool. Now we're going to plug in x equals 3. All right, that will cancel out this one. So b times 3 minus 2 equals 7 times 3. All right, b times 3 minus 2, which is 1. So b is just going to equal 21. So we can add another equal sign. We can bring this up and this up. So a equals negative 14. B equals 21. So now we sub this a value into here. We sub this b value into here. Integral negative 14 over x minus 2 plus 21 over x minus 3. These are equivalent. This is called partial fraction decomposition, which is where we take some sort of x value over a factored quadratic. You know, we have x squared minus 5x plus 6. This is our factored quadratic. We take this, and then we can split it up into this. So now, what we know from before with our ln tactics and with our constant tactics, this is negative 14 integral of 1 over x minus 2 dx plus 21 integral 1 over x minus 3 dx. Okay, so now we have the ln like relationship here, where we have no coefficient on the x. So negative 14 ln of x minus 2 plus 21 ln of x minus 3 plus c. And this is our final answer. So this is a lot of work for one of these problems. But this, again, there will always be this on the problem. So I'm going to give one more partial fraction problem, and this is an advanced one. So if we have x squared plus 4, all right, and then we have 3x squared minus 4x, or 3x cubed, sorry, minus 4x squared minus 4x. Okay. So now, this might not initially look like a partial fraction. This might look like a U-sub kind of problem, but if you try it out, U-sub is not going to work here. So, how do we decompose this into a bunch of separate fractions? Well, first of all, we need to factor the bottom. So we will have x, and then you have 3x squared plus 4x minus 4. This, with factoring, is factored into, I believe, 3x minus 2, and then x plus 2. So 3x minus 2, and then x plus 2 dx. So now, we have 3 factors here. Okay, so we need to split this up. A over x plus b over 3x minus 2 plus c over x plus 2. Okay. So now we need to get rid of these denominators. I'm going to set it equal to x squared plus 4 after. So how do we get rid of these denominators? We'll multiply everything by x. So a plus bx over 3x minus 2 plus cx over x plus 2. Okay. Multiply everything by 3x minus 2. A times 3x minus 2 plus bx plus cx times 3x minus 2. Okay, and then now multiply everything by x plus 2. So then we have a times 3x minus 2 plus bx times x plus 2 plus cx times 3x minus 2. Wow, that is a lot of work. So when you have something with these 3 denominators like this, you can actually just put these 2 denominators with the a, put these 2 with the c, and then put these 2 with the b. Does that make any sense? Or you can multiply it out like I just did. So now we have this equals x squared plus 4. Okay, so now we can find our a value by using the common factor here. There's an x on the b term and an x on the c term. So that means when you plug in 0, that b and that c is going to go away, and you'll only be left with the a. So we have a times 3 times 0, which is 0, minus 2, and then the x plus 2 term, which I forgot on, wow, both of these. Or no, just this one. Anyways, times 0 plus 2, which is 2. Okay, 0 crosses this out, 0 crosses this out. 0 into here is 0, so this equals 4. So negative 4a equals 4, and then a equals negative 1. Right. Let's put that value to the side. Okay. Now, we can say that since this term has 3x minus 2, this term has 3x minus 2. If you plug in x equals 2/3, then you're going to end up canceling out the a and canceling out the c. So let's do that. b times 2/3 plus, or times 2/3 plus 2. So 2/3 plus 2 is going to end up being 8/3. So times 8/3 equals 2/3 squared is 4/9 plus 4. So 4/9 plus 4 is 40/9. Okay, now we have b times 16/9 equals 40/9. Now times both sides by 9/16 to cross this out. And then you end up getting 40/16, which simplifies to 5/2. Okay, so we're going to take this stuff, move it to the side again. Now we have our c value. So, again, plugging in negative 2 will cross out this one and this one. So we have negative 2c times 3 times negative 2 is negative 6 minus 2, so negative 8, which equals negative 2 squared, so 4 plus 4. So we have 16c equals 8, c equals 1/2. All right. After all that work, we finally have our values. So I accidentally erased it earlier, but we originally had a over x plus b over 3x minus 2 plus c over x plus 2. So now this gets factored into negative 1 over x plus 5/2 times 1 over 3x minus 2 plus 1/2 1 over x plus 2. Wow. Again, a lot of work for one problem. So this, negative 1 integral 1 over x plus 5/2 integral 1 over 3x minus 2 plus 1/2 integral 1 over x plus 2. I'm leaving out the dx's for now, don't do that. But I am, just to go through things quicker. So, negative ln of x plus, if you u-sub here, you get du over 3 equals dx, because the derivative of 3x minus 2 is 3. So, we're going to say 5/6, because we moved that 1/3. So 5/2 times 1/3 is 5/6. That's where I got that from, just to let you guys know. ln 3x minus 2 plus 1/2 ln x plus 2 plus c. So, more than 5 minutes on this one problem, likely. You will always have a partial fractions. It can be easier than this, or it can be of this difficulty. It's usually not going to be harder than this. And it is usually a multiple choice question. So, that is partial fractions, and finally we're on our last topic, which is improper integrals. So what makes them improper? Well, very discriminatorily, if it has an infinity in it, it is considered improper. So, on an FRQ, if you have the integral from, let's say, 0 to infinity of a function, every single time you write this out while you are solving it, you will have to put limit as b approaches infinity from 0 to b f of x dx. Which means that even when you solve it, when you do the second fundamental theorem of calculus, you have to write limit as b approaches infinity, f of b minus f of 0. You have to write this too. You always keep the limit as b approaches infinity. So, how do you solve an integral at infinity? So, let's take something simple. 0 to infinity, or I should be writing limit as b approaches infinity of 0 to b of x dx. I'll do 2x. Then you get x squared. I'll gotta keep the limit. You get points off if you don't keep the limit. So x squared from 0 to b. And then, as you would expect, if you go to infinity, the area under x squared is going to be infinity. So you have b squared minus 0, and infinity squared is infinity. So that intuitively makes sense. You have a function. The y value goes to infinity, so of course the area value is going to go towards infinity too. Alright, so what would make a function not have infinite area when it goes to infinity? Well, there's pretty much one condition that must be true, which is that as it goes to infinity, the y value has to be 0 at infinity. It just has to be. If it's anything more than 0, let's say the y value is 1, the lowest y value is going to be 1. So if you go from infinity times 1, because if you have like a y value of 1 all the way over, infinitely long y value of 1, infinity times 1 is going to be the area of this, which is still infinity. So the y value must be 0. Otherwise, it diverges. That means it goes to infinity. So let's look at a few. Let's look at 1 over x. From 0 to infinity. Alright. So, to integrate this and figure out if it diverges or not, we have to, first of all, take the integral, which is ln of x. We know this. So, ln of x from b and then 0. Alright. So, what is ln of infinity? It's infinity. So, believe it or not, the integral of 1 over x as it goes to infinity, I should have written from 1 to infinity, because 1 over x is not defined at 0. But the integral from 1 to infinity is infinity. This area does not converge to a single number. It will be infinite. So that tells you that it does not slow down enough. That's another condition. If it decreases fast enough, then it will have a convergent number. But if it does not, such as 1 over x, it kind of gradually decreases, then you will have infinite area under it. So, I'm going to tell you right now that this function, e to the negative x, does have a value. So, let's figure it out. Integral from 0 to infinity of e to the negative x is the limit as b approaches infinity, negative e to the negative x. Alright, so this is the same thing as saying, and I'm just going to duplicate this because I really don't feel like continually writing it, as negative 1 over e to the b plus 1 over e to the 0, right? Second fundamental theorem of calculus. Alright, so this will actually equal 0, because as 1 over anything to the infinity if it hits infinity, 1 over infinity, it is 0. So this term crosses out, and the area here is just 1 over e to the 0, or just 1. So believe it or not, the integral from 0 to infinity of e to the negative x is 1. This entire thing, even though it goes all the way to infinity, the area under the curve is only 1. So let's look at one final example. 1 over x ln of x. Say, we know that 1 over x is divergent, has infinite area. But x ln of x, we're going to go from 2 because ln of 1 is 0, so it doesn't exist. Alright. So, how would we integrate this? Well, first we need to actually integrate it. X ln of x can be written as x times u. We're going to u-sub this ln of x. So x u equals ln x. Du over 1 over x equals dx, because the derivative of ln x is 1 over x. So this is going to be x dx. Cross out these x's. 1 over u du equals ln of u, which is ln of x. That is our answer for the integral of x ln x, which I think is pretty cool. So, doing that work down here, we have limit b approaches infinity of ln of x from 2 to b. This, plug infinity into here. Ln of infinity is infinity. Ln of infinity is the same thing as saying ln of infinity, which is infinity. So even though, I'm going to say it's infinite or diverges, even though 1 over x ln x is less area than 1 over x, because x times another number on the denominator is going to make it smaller. It is still infinite area as it goes to infinity. So, many questions you might be asked on the test. Again, for the BC test, there's always one improper integral question. You might be asked to find the area or state that it diverges. If you have it on an MCQ, then that's fine. Just figure it out. And if you have it on FRQ, do not forget your limit as b approaches infinity. Alright. So, that was a long unit. So let's recap. We've discussed that area under a rate curve is the total amount of the rate. So if you have the rate at which water enters a tank, then the area under that rate curve is going to be the water that entered the tank, the total amount of water. If you have the rate at which snow falls onto a house, then the area under that rate curve will be the total amount of snow that fell onto the house. There is always problems about it. Multiple, you need to know that. Then we have Riemann sums. This is a big topic. Midpoint sums are relatively rare, but left, right, and trapezoidal Riemann sums will always be asked on the test. There's always an FRQ where you need to do Riemann sums, and there's always at least one multiple choice question where it's going to have you do some sort of Riemann sums. Next, you need to know how to convert them to integrals when they go to infinity. So there is sometimes not, a question on the test where you need to convert them. And then you should also know integral rules. So the fact that addition and subtraction do not conflict with integrals, you need to know that. And then the fact that you can't multiply or divide normally. And then the fact that negative b to a is equal to the same thing as a to b when b is greater than a. You need to know that you have to flip those and add a negative sign. You should know your fundamental theorem of calculus, especially that d over dx of an integral from a to u equals f of u times u prime. This relationship, very often on the test and very often forgotten by people on the test. Then you need to know how to integrate. So power rule, obviously, but that's easy. And then U sub. There is always a U sub question on both the AB and BC tests, sometimes multiple. And then finally, for BC, you need to know integration by parts and then partial fractions. And then you need to know improper integrals, which you have to write limit as b approaches infinity. That is it for Unit 6 integration. Thanks for watching.